Hi, this is Alex from devstories.eu, Python, Cheminformatics, and AI, episode 18 of 22. Why ask an algorithm to generate a million random keys and test them one by one when it could just look directly at the lock and forge a custom key right inside the keyhole? Traditional drug discovery often relies on generating vast libraries of candidates and filtering them down, but that wastes immense computational resources. Target-aware generation and docking solves this by directly utilizing the three-dimensional geometry of the biological target to build or place molecules. In these generative tasks, we are working entirely in 3D geometric space. Target-aware generation, also known as structure-based drug design, builds a new molecule based directly on the 3D structure of a target binding pocket. Take a concrete scenario involving a viral protein. This protein has a highly specific geometric cavity. Instead of generating molecules in a vacuum, a conditional diffusion model analyzes the exact spatial boundaries and chemical properties of that cavity. It then custom grows a novel ligand structure directly inside the pocket. The model starts with a cloud of noisy 3D coordinates and atom types located within the binding site. Over successive steps, it denoises this cloud. Because the generation is conditioned on the target pocket, the model places atoms and forms structures that naturally complement the cavity, aiming to guarantee high interaction affinity. Here is the key insight. The algorithm does not just guess a shape, it explicitly learns the spatial relationship between the target and potential binders. Some approaches even incorporate interaction-based retrieval, pulling data from known high-affinity ligands to further guide the generation of these target-specific molecules. That covers generating a completely new molecule from scratch inside a pocket, but you will often have an existing molecule and need to know exactly how it interacts with a biological target. That brings us to molecular docking. Molecular docking predicts the binding pose to assess binding affinity and specificity. In a diffusion framework, models take a known molecule and a target structure as inputs. Instead of generating chemical identity, the diffusion process operates purely on the spatial orientation of the molecule. The model starts with the ligand in a random, noisy 3D pose and iteratively denoises it. It refines the spatial coordinates of the molecule until it settles into the correct binding configuration inside the protein pocket. Advanced docking models take this a step further by treating the target itself as a flexible entity. A model called redock uses a technique called a diffusion bridge to predict the binding poses of the ligand while simultaneously modeling the movement of the pocket sidechains. This creates a realistic, flexible docking scenario where both the ligand and the target adopt to each other during the prediction phase. The critical shift here is that diffusion models have moved structural drug design away from rigid, isolated approximations. By treating both the generated ligand and the biological pocket as a continuous, adaptable geometric system, the model natively outputs molecules and poses that are physically grounded in the precise reality of the target environment. That's all for this one. Thanks for listening, and keep building.